So the next topic, the next two speakers are involved in a topic that I would call combinatorial number theory and classical modular functions. Freeman's earliest works, well, maybe his paper number 4 according to his publication list, is on this topic. It's on the topic of partitions, which Freeman returned to many times in his life. He describes it as even as a means of relaxing to look at these old ideas that go back to Euler and Ramanujan. This has been well documented in many places, but on Ramanujan's deathbed, he pointed to certain modular type functions that he called, I think, Mach theta functions, which turn out, as you'll see today, to play a critical role in understanding the kind of question that Freeman was interested already in this very first paper. So one of the key functions in the study is called the partition function. Any integer n, you partition it into parts, and you count how many ways you can do that. It's called P of n. And it's closely related to classical modular functions. And Ramanujan made many great insights about this function, many conjectures. In particular, one that Freeman picked up, I think, in high school, is a divisibility property of these functions along certain very special arithmetic progressions. And like a good deep thinker that he is, he was not satisfied that these numbers were just divisible by some other numbers, but he wanted to explain why, from grouping partitions into partitions, it should be quite easy to explain it that way, in a more physical way even. And to do so, he introduced a notion of a rank of a partition and a term, I think it's co-rank, but now called crank, which I don't know, which then became central in many studies. He put forth some numerical evidence and conjectures which were solved by his good friend Oliver Atkin, Peter Swinnerton Dyer, Garvin, Andrews, and many others. And this subject began to thrive after this 1942 paper of Freeman, which, according to his writings, were even, he had this idea already in high school. About 10 years ago, and this is one of the reasons we chose this topic amongst all Freeman's contributions, a Dutch mathematician by the name of Zweigers, in a rather remarkable thesis, revisited these exotic Mach modular functions that Freeman and others were able to see aspects of, but he was able to turn the theory into a much more familiar theory, looking much more like an ordinary modular function. And with that, the door opened to solve many of these long-standing questions that were raised by Ramanujan and Dyson. And you'll see some of these today. Remarkably, these Mach modular, or Mach theta functions is what he called them, these Mach theta functions have entered into physics, into string theory, into other aspects of group theory, and they have become a central part. And so our choice of the topic was one which is again very active today, and the speakers that we have chosen are the leaders in this field. Dyson describes this general area as a beautiful garden created by Ramanujan, and one of the great gardeners in this garden is George Andrews, and so it's great to have him here. I would say Dyson has created a much bigger thing than a garden, a zoo in which frogs jump around. And we all like to be just zookeepers in his zoo. So our first speaker, I had the idea that after the talk we could take 2 quick questions, and since the last time I apparently was very quick, we'll try to finish by about 12:15 to give 15 minutes of general discussion of mathematics, especially these topics, but anything else that might come up. And then we'll break at 12:30. So our first speaker of this next session is George Andrews from Penn State University, and his title is Partitions, Dyson, and Ramanujan. George.
Thank you very much, Peter. It is a huge honor to be able to participate in this event honoring my good friend Freeman Dyson. This is very special to me, and I'm very pleased to be here. To start my discussion, I thought I would turn to a book review that Freeman wrote. It had sort of the quintessential Dysonian elements about it. It's a review of the book Nature's Numbers, and it starts out, "This book describes in clear and simple language a view of mathematics with which I profoundly disagree." And I thought, I'm just going to love this. So I moved down the page, and I've come to this line. "I disagree with Stewart when he makes negative comments about old-fashioned non-visual mathematics, the mathematics of equations and exact solutions." And I thought, fantastic. And I moved on, nodding with agreement as paragraph after paragraph wafted by, and eventually came to the end, and things started to not resonate in quite the same way as I got to the last couple of paragraphs. The disagreement between Stewart and me is mainly a matter of taste. My mathematical tastes were formed at a time when the most common adjectives in mathematical conversations were deep and trivial. First-rate mathematics was deep, all the rest was trivial. Logical depth was the essential virtue that we had looked for in mathematics. And he speaks finally of Stewart's examples. His examples are well chosen to illustrate the power of mathematics to bring processes from population biology and embryology and meteorology into a unified picture. For me, an old-fashioned analyst, these examples are visually interesting but mathematically trivial. I miss the depth complex analysis brought to number theory, the depth that Lie algebras and fiber bundles brought to physics. So the reason that these last few paragraphs, at least, caused me to stop just letting them pass by with pleasure is because the topics that I'm going to relate this morning, the work of Freeman that has most profoundly affected me and many others, is certainly not deep in the sense that one will be able to describe his discovery and what he had achieved in fairly straightforward, easily understood basic mathematical terms. And yet the impact of it has been so substantial that the word trivial seems totally inappropriate. So I don't know exactly how to classify this, but I will at least describe 4 topics that seem to me to collect 4 topics where Freeman has had a significant impact on mathematics and on this area of mathematics, and yet the words both deep and trivial somehow do not fully, are not really applicable to what he has achieved. So I'm going to talk about his first paper, I think written when he was 18 or 19. Then the paper that Peter just alluded to, Dyson's guesses in partitions, and then a particular conjecture of his, and finally something that in partitions that he called the adjoint. So the first topic has a surprising history. It goes back to the Indian mathematician Srinivasa Ramanujan and discoveries that he made, and also to the work of a much less known mathematician, Leonard Rogers, who, if you last long enough, you get caricatured in the student newspaper. And this concerns what are called the Rogers-Ramanujan Identities. So let me tell you what these are. These are 2 identities relating infinite series and infinite products. They are reasonably simply stated. So the infinite product that you see here, the exponents on this variable q, you will see me going back and forth between using x and q for the variables in the functions I consider. In this, the exponents are the numbers 1, 4, 6, 9. Every integer whose last digit is 1, 4, 6, or 9 is what is in this sequence, or the numbers congruent to plus or minus 1 mod 5. And here you see an infinite series where the denominators are these increasing size of products, 1 minus q squared. In the nth term, it will go up to 1 minus q to the n. And the exponents are the perfect squares, 1, 4, 9, 16, etc. In the second identity, the second Rogers-Ramanujan identity, you see these exponents are the numbers whose last digit is 2, 3, 7, or 8, they can be described as the numbers congruent to plus or minus 2 mod 5, and these exponents are the numbers of the form n times n plus 1, 2, 6, 12, 20, etc. So, as in 1940, in a book that the young Freeman Dyson also looked at, was an account of the discoveries of these identities. Carty is talking about Ramanujan, and he says they were first found by Rogers in 1894, a mathematician of great talent but comparatively little reputation, now remembered mainly for Ramanujan's rediscovery of his work. Rogers was a fine analyst whose gifts were on a similar scale, not unlike Ramanujan's, but no one paid much attention to anything he did, and the particular paper in which he proved the formulae was quite neglected. So Ramanujan's story will be succinctly described. He was born in poverty in southern India, and in around 1912, 1913, he had done many surprising things in mathematics. He wrote to Hardy, and in one of the letters that he sent were these formulas, which, as we will see, he did not know how to prove at the time, and Hardy, in looking at them, could not prove them, and sent them to several of his friends. Rogers, being at Leeds, was not in the inner circle and not one of the people to whom these identities were sent. No one could prove them until Ramanujan, in thumbing through a 20-year-old volume of the Proceedings of the London Math Society, found them there in this paper of Rogers entitled Second Memoir on the Expansion of Certain Infinite Products. Apparently no one had really slogged through even the first memoir, and consequently Rogers remained in obscurity until this event, at which time he shortly thereafter became a Fellow of the Royal Society. You always do well when you solve a famous unsolved problem, and when you do it 20 years before it's posed, your reputation really takes off. Ramanujan discovered the formula sometime before 1913. He had no proof and knew that he had none, and none of the mathematicians to whom I communicated the formula could find one. So one of the things that is interesting in the history of this is to note that Ramanujan actually sent Hardy a long letter, which starts out as follows. You won't be able to read much of it, but the reason I put it on the screen is to show some people have questioned whether Ramanujan knew whether he had a proof of something or not, since his training was highly unorthodox. But in this fairly long letter, Ramanujan starts by saying the reason for taking these series to be equal as product are the following, and then he goes through a variety of asymptotic analysis, of actual expansion of the series, as he does in the next page of his letter, and so on, so that he clearly knew he couldn't prove these formulae, but he had a large amount of empirical evidence that they were actually true. So let me return to Hardy's description of this. They are therefore stated without proof in the second volume of McMahon's combinatory analysis. And so McMahon was the English combinatorialist who did various important work in purely combinatorics and wrote a large two-volume memoir called Combinatory Analysis, and in the second volume, chapter 3, is devoted entirely to these identities. Mr. Ramanujan of Trinity College has suggested a large number of formulae, and here are two, and he lists the first one in the middle of the screen here. He says, this most remarkable theorem has been verified as far as the coefficient of x to the 89th power by actual expansion, so there is practically no reason to doubt its truth, but it has not yet been established. So after all of this, this became really quite a famous problem. And Hardy goes on, the mystery was solved trebly in 1917. In that year, Ramanujan, looking through old volumes of the PLMS, came accidentally across Rogers' paper. I can remember very well his surprise and the admiration he expressed for the Rogers' work. And then Hardy goes on to describe the subsequent history of this, and up to the time that Hardy was writing in 1940, there had been actually 5 proofs produced by Watson, Schur, and Rogers, and Ramanujan also produced further new proofs. So one of the books that clearly influenced the young Freeman Dyson was the Introduction to the Theory of Numbers by Hardy and Wright, and also the book called Ramanujan, which was basically a compilation of Hardy's lectures to Harvard University in 1940. And in this book, Hardy wants to give a picture of the achievements that Ramanujan made, and in particular, he devotes a chapter, but 2 pages that I want to focus on to a proof of these identities. Well, this looks like fairly complicated mathematics, but I put it on the screen because I just want you to see the form of things. He is basically mimicking or copying with slight variations the second or third proof that Rogers gave of these formulas, which is elementary in scale, but completely unmotivated in that he takes 2 forms out of classical theta function theory, which gives 2 different Fourier series expansions of a given function, and then he makes the surprising statement right in the middle of the screen here that he takes this Fourier series, and now he says we have 2 different expressions here, and so we're going to replace the appearance of the trigonometric functions, the cosines, by certain expressions of this nature. He worries a little bit about whether this is totally rigorous and goes on to deal with it later in the chapter. The point is, it is totally rigorous, and all of a sudden, right at the bottom of the page, he winds up with something that is effectively equivalent to the Rogers-Ramanujan identities. In order to be more succinct about what is actually going on here, I want to summarize what he actually was saying, namely, what the secret of what's happening here is to take an infinite series problem, which you see in the middle of the screen, and instead of trying to do it directly, what you do is to establish a certain relationship between 2 sequences of rational functions, namely the pairing that you see at the top of the screen. But the thing here, this equation is, of course, there are an infinite number of these as n runs from 0 to infinity, but each expression is a finite expression. And to solve the first Rogers-Ramanujan identity, what you need to show is that if you choose beta n to be this finite product, and alpha n to be this much more simple expression in just actually involving just 2 terms, that these 2 things satisfy the expression at the top of the screen, and therefore they fulfill this, and from this almost immediately follows Rogers-Ramanujan. Now, seeing all this, one naturally thinks, or not necessarily one, but the young Freeman Dyson naturally thought, There must be other things of this nature, and in his explorations, I suspect, although he will have to confirm or deny this, I suspect he discovered that there was a formula exactly of this nature related to the number 7, precisely in the way that the Rogers-Ramanujan identities are related to the number 5. Upon further exploration, he would have determined that Rogers, buried deep in the 1894 paper and in another paper as well, and a young Atlee Selberg actually had found these formulas. And so the first sentence of his first paper reads, "The subject of this paper is a set of 3 identities proved by Rogers and by Selberg independently." Then he describes his notation, which is the first formula that you see here is the one that I just put on the screen. And his proof then is a significant simplification and clarification of the way Hardy, copying Rogers, proved the Rogers-Ramanujan identities. In particular, he now eschews the use of the trigonometric identities, replacing the e to the I theta in the cosine of theta by just z, and consequently things become much easier. But in following out that proof, he is able to prove the relation between the alphas and the betas purely using an argument of mathematical induction. So here, this cannot be considered really a deep paper, and yet I suggest that it had a profound impact on subsequent research. In particular, an older British mathematician, W.N. Bailey, was clearly impressed with this paper and saw certain things in it that caused him to write a follow-up paper and submitted it to the London Math Society, and Hardy was the editor involved, and the only obvious person to referee it was Freeman Dyson. And so rather than maintaining the anonymity of the referees, as is usually appropriate to do, Hardy had them correspond about this, and here is supplied to me by Freeman. The first of the letters that Bailey sent to Dyson: "Dear Dyson, I'm writing to you in connection with my paper for the LMS. I had a letter from Hardy 2 days ago, and he enclosed your report, a rather unusual thing to do, but very useful in the circumstances. Many thanks for your comments," etc., etc., etc. And what Dyson did was not only provide comments, but provide a number of further formulas of this very general nature. And the most interesting thing in the letter is what happens right toward the end. Bailey says, "With regard to your formula for products in which the powers of x advance by 27, I'm afraid I don't see how you obtained them. I should very much like to know the products in the first 3. The products in the first 3 are occurring in my formula for 9s with x replaced by x cubed, as I suppose you noticed. If you like, you could make a short paper about them, or if you don't think it worthwhile making a separate paper, I will incorporate the formula in my paper with due acknowledgments." And so basically he's saying, you have bested me. Of course, anytime you write to someone and say, you have bested me, it really puts a burr under your saddle. And so 2 days later, Bailey writes, "Just a line to tell you not to bother writing out proofs of your identities. If I'm not already too late, I have rather belatedly found out how you got them." And so Dyson's paper really set off the work by Bailey. The formula that Dyson was referring to, sometimes called I think someone has quoted Dyson as saying this was his favorite formula of this nature, but in any event, this is of the same style as what we've seen before, but now if you write it exactly as he did with the sevens, you now have 27, and you can collapse this into this infinite product. So, in the first talk this morning, we heard about a subject going temporarily to sleep, and Bailey's student, Lucy Slater, sort of wrote a paper that was soporific in the sense that it had 120 formulas, one after the other one, without anyone really being able to see why you would be interested in the 75th as opposed to the 76th. And in the culminating paper in this series, Bailey wrote, this is one short section from his paper, basically the first paragraph gives a recipe and complete and accurate directions for how to do something. He says, these values of delta and gamma reduce to the previous values when n tends to infinity. In other words, reduce to all of these Rogers-Ramanujan type formulas. We are, however, and lead to more general results, but these lead to more general results involving only terminating basic series. We are, however, more concerned with identities of Rogers-Ramanujan type in this paper, as the most general formulae for basic series, apart from those already given, are too involved to be of any great interest. And with that, he dismisses what he had written there. And so it took more than 40 years before someone actually followed up on his recipe. So let me return to this relationship between these sequences of rational functions. These alpha and beta are called a Bailey pair if the sequences of functions are related by this relationship. And what Bailey gave the recipe for, but was too embarrassed or diffident to actually state, was what is now called Bailey's lemma, which is that if alpha n and beta n is a Bailey pair, then so is a further expression that is another Bailey pair. In other words, what Bailey was saying was that there is, without realizing it clearly, is that there was this, an iterative, excuse me, fortunately I still survived. I guess every speaker has to deal with something like this. I'll remember not to back up too far. So the point is that you have this huge iterative power. In other words, from a given pair, you can produce another pair. And the impact of this particular aspect of this work in, say, applications in statistical physics has relied fully on this short paragraph where the recipe was given for this tremendous iterative structure that, owing to the fact that perhaps Bailey was much less willing to think outside the box than Dyson has been, he did not choose to write down the implications of his recipe. So that's what I want to say about Dyson's first paper. Now I want to go to the topic alluded to by Peter in his introduction, which is to deal with the number of partitions of n. So P of n is the number of ordered sums of positive integers that add to n. So P of 4 is equal to 5, and I've listed the 5 partitions of 4. P of 5 is equal to 7, and I've listed the 7 sums that add up to 5. And in his fifth paper, which was published in the undergraduate math journal Eureka, when he was an undergraduate at Cambridge, Freeman titled his paper, Some Guesses in the Theory of Partitions. And the divisibility property, the divisibility theorems of Ramanujan are listed right now at the bottom of this page, namely that this partition function, when the sequence is 5n plus 4, this is congruent to 0 mod 5. when P of 7n plus 5 is congruent to 0 mod 7, P of 11n plus 6 is congruent to 0 mod 11. And as was mentioned, what Dyson was interested in is the question of, all right, P of 5n plus 4 is always divisible by 5, and the proofs of this are ones that certainly might reasonably be called deep in some sense, but they give you no understanding of why, down at the nitty-gritty level, you could actually split these sets of partitions up into 5 equinumerous classes. And so what Dyson does is to say, after various experiments he's done, that he defines the rank of a partition, which is the largest part of it minus the number of parts. And he says, all you need to do is classify the partitions according to the remainder modulo 5 of the rank, and that will split the partitions of 5n plus 4 into 5 equal classes. And also it will split the partitions of 7n plus 6 and 7n plus 5 into 7 equal classes. So let me give you one example. Here are the 30 partitions of 9, and although they don't all fit on the screen simultaneously, I have a little advantage over people who are using a beamer in that I can move my picture around so you can see what I'd like you to see, and in case the top 2 things go out, I still can get something in on the bottom. But this provides you with these splits, so that, for example, here's the partition of 9, 7 plus 1 plus 1. The largest part is 7, the number of parts is 3, and so the rank is 4 mod 5. And indeed, here you have largest part 3, there are 4 parts, so the rank is minus 1, but minus 1 is also congruent to 4 mod 5, so that's why it's listed there. And you see these 5 classes with 6 partitions in each class. Indeed, what the ending of Freeman's paper is particularly appealing, because he observes that while he can deal with all of the 5s and the 7s, when he deals with the 11n plus 6, the rank doesn't do the trick. And so he says, I hold that there exists an arithmetical coefficient similar to but more recondite than the rank of a partition. I shall call this hypothetical coefficient the crank and denote it by capital M, and then he, even though he doesn't know what this function is or even conjecture what it is, he does describe various things that it's supposed to satisfy. And whether he says at the end, whether these guesses are warranted by the evidence, I leave to the reader to decide. Whatever the final verdict of posterity may be, I believe the crank is unique among arithmetical functions in having been named before it was discovered. May it be preserved from the ignominious fate of the planet Vulcan. So let me say, in terms of the previous slides that you've seen, what Freeman eventually did was to figure out that the generating function for the rank, he did not write down this particular equation, but I write it down because you will see in, I believe, in Catherine Bringman's talk, that this is one of the foundation stones for the subsequent work on the Mach theta functions, which for a long time after Freeman's conjectures, no one really drew significant connections between his work on the rank and these modern achievements with regard to Mach theta functions and the Mach modular forms. So I will leave to her an explication of those further developments, but I do want to continue this with one aspect of a partition theorem, namely, Euler proved that the number of partitions of n into odd parts equals the number of partitions of n into distinct parts. And so this is the obvious, correct assertion when n is equal to 6. Here are the sums with odd sum n's. Here are the sums with the distinct sum n's. And as Euler predicted, they're exactly the same number of each type. I want to point out that Euler's proof is slick and quick, because this is the generating function for partitions with odd parts. This is the generating function for partitions with distinct parts. The middle formula, on the one hand, all the even exponents cancel out all the even exponents in the denominator, leaving you with the odd exponents. On the other hand, algebra allows you to cancel each factor into the numerator, leaving you with these factors. And so Euler undoubtedly found this proof before he found his theorem. But surprisingly, not long after Dyson's discovery of the rank, Nathan Fine refined Euler's theorem to state that the number of partitions of n into odd parts with largest part 2m plus 1 equals the number of partitions of n into distinct parts with rank 2m or 2m plus 1. And so Fine is in a similar way to Dyson splitting up the partitions of P of n. He's splitting up Euler's partitions now into these subclasses, where in this case, in this example, we use odd parts with largest part 3, and here are the partitions of I like this. I must not step back when I like a theorem. Here are the partitions of 9 in distinct parts where the rank is either 3 or 2, which coincides with Fine's theorem, so that Dyson's work had this effect on subsequent combinatorial work, and I will return to that later at the end of my talk. So I want now to turn to what I call Dyson's conjecture. Dyson's conjecture asserts that the constant term in the expansion of this expression involving n variables, x1 up to xn, where you are given fixed integers, non-negative integers ai, is equal to this quotient of factorials, which is the familiar multinomial coefficient involved with a1 plus a2 plus an. So this occurred at the end of this paper, which is also in his collected works, Statistical Theory of the Energy Levels of Complex Systems, from the Journal of Mathematical Physics. He proves a number of cases of this, and indeed, very quickly after the appearance of that paper, Gunson and Wilson proved it, and then 7 or 8 years later, Jack Good proved it. And I want to show you, so the question now, the proofs by Gunson and Wilson would perhaps qualify to be called deep in the sense that Dyson was talking in the review of Nature's Numbers. However, Good's proof is elegant, but surely can't be called deep. Good says, let's let this product of these xi's be this f, and the cn be the constant term. And then he makes a very simple observation, namely that if you set all the a's equal to 0, everything is 1, and there is only a constant term. Furthermore, if you set an a equal to 0, it effectively eliminates the effect of that corresponding x from affecting the constant term, and consequently, you can drop to the previous case by when you set a particular AH equal to 0, you drop down one level from n to n minus 1. And then Good makes the following observation, which looks quite complicated until one talks through it. Good says, next we observe this identity is true, but this is obvious, he said, because the expression on the right-hand side, each term is a polynomial in the variable x of degree n minus 1. and this polynomial n times equals 1, namely when I set x equal any of the xi's, all the terms cancel except the ith term, which is equal to 1. So any polynomial that assumes a value more than its degree is equal to that value. And so this is just simply has to be equal to 1. Setting x equal to 0, and doing a little algebra, you reduce the expression that he just had to this. And now if you multiply through by capital F, each term here cancels out by 1, lowering by 1 the order of the A, and therefore the constant term must satisfy this recurrence as well, and the constant term, it thus satisfies this same recurrence, and consequently the initial conditions and the recurrence uniquely define Cn, but the multinomial coefficients satisfy this recurrence, and consequently the constant term is this. So just this clever insight by Jack Good allows one to see, there's nothing to it at all. Not really a fair statement, even if one thinks of the significant implications that the original conjecture had in physics, but also, of course, with a number of people around interested in constant terms, you form something like the series and the products and the finite products that appear in Rogers Ramanujan, and you obtain what is called the Q analog of Dyson's conjecture, which was originally solved by Doron Zeilberger, who's in the audience today, but has a variety of significant implications connected with, say, the work of Ian MacDonald on what are called the MacDonald identities, of which there is a long, interesting and charming story in Freeman Dyson's paper, Missed Opportunities, where his contacts with Ian MacDonald were on a social basis, and they never mentioned that both of them were working on exactly the same problem at that one time. The last topic that I want to talk about, I should say that a variety of things have arisen extending this theorem that originally is due to Zeilberger to a variety of things connected with Lie algebras, and thus qualifying as quite deep mathematics. In the late 1960s, Freeman Dyson again returns to the theory of partitions and to looking at some very simple questions. And he finds a new symmetry in partitions. The article begins as follows: the rank of a partition of an integer into integer parts is defined as the greatest part minus the number of parts. That's from his original paper on the guesses. If P of Mn is the number of partitions of n into positive integer parts with rank m, then there's a well-known symmetry of partitions called conjugation, which interchanges the greatest part with the number of parts, and thus the number of partitions with rank m equals the number of partitions with rank minus m. So let me tell you what the conjugation is, because it's a very simple construct. Namely, here is a partition 7 plus 5 plus 5 plus 4 plus 3 written in what's called the Farrer's graph. So there are 7 dots in the first row, as you see, connected by the blue lines, 5 in the second, 5 in the third, 4 in the fourth, 3 in the fifth. And what the conjugation does is to replace the blue lines horizontally by blue lines vertically, and now you read the conjugate by collecting the dots in the vertical lines. So they're 5, 5, 5, 4, 3, 1, 1, and that is called the conjugate partition. And as you see, the largest part of the number of parts have been interchanged in this operation. So he says, well, suppose we now look at Q of Mn, the number of partitions of n, into non-negative integer parts with rank m. And so if few people think about looking at partitions with non-negative parts because you can throw in 0 as much as you want to, and thus there are infinitely many partitions of n into non-negative parts. But if you require the rank to be the largest part minus the number of parts, you can't throw in zeros forever and you can't have more zeros than m. So this means that q of mn will be a finite quantity. And he makes several observations about it, but the observation that I want to point to most is that he then computes the table of both the partition function without extra parts and the partition extra zeros and the partition function with zeros. So here is the table that he produced, and he noted that P of m and minus m are the same. So as expected, there is perfect symmetry around the line, the column related to 0 because of this relationship. But now you go down to this next table that he's computed for Q, and you don't immediately see a symmetry, but if you're as smart as he is, you pick up very quickly that there is sort of an angular symmetry. In other words, all the 2's are here, and then they go like that. Here is a row of 3's, and then it goes with a 2, and then the 3's repeat down like that. Here you have 5, 5, 4, 4, 4, and the 5's go down like this. And so his question that he answers in this paper and uses to good effect is there something like conjugation that actually produces this symmetry? And what he says is that we'll give a simple combinatorial. This is the symmetry now written in terms of an equation. And he says we can define the adjoint of a partition as follows. Well, instead of reading through his definition, let me show you how you produce the adjoint. What you do is as follows. Here, the rank is 7 minus 6. What he first does is to add a new column of dots to the left. The little circle here, rather than a dot, comes from the 0. I want to distinguish that it's not going to be one of these dots that adds up to the full partition. What he does is to add a new column of dots to each row, even to the row with the little 0 in it, and then he removes effectively the top row, and now he looks vertically at what is remaining, and if the top row left something empty, you put new zeros out there, and you forget about this 0, and what you have is what he calls the adjoint of the partition, and what has happened is exactly the symmetry that he wanted, which goes from this horizontal to this angular line, and with the rank changing from +1 to -3. The reason I choose to end on this note is because if I mentioned at the end of the proof of Eulers' theorem that there was this refinement done by Nathan Fine, which basically gives you a new assertion that it refines Eulers' theorem. There it is again. And the adjoint of Dyson's adjoint allows you to understand combinatorially, in the way Dyson wanted to understand Ramanujan's partitions, partition divisibility, allows you to understand this combinatorially. And so briefly, going through this is as follows. I start out with the partition of 5 plus 3, and I perform Dyson's device. Namely, I put in these x's. Oh, and I put an extra thing in if the rank is odd. In this case, the rank is 3. I need even rank always, so I put in an extra 0 in order to make the rank odd. I then kill this and put all the real remaining parts down here, noticing that I've dropped 3 parts in moving from this line to this line. And I keep playing exactly this same game. And if I move from this line down to the next line, I have dropped 3 units again. If I do the adjoint process again, I drop only 1 this time. And finally, I wind up with this. And so Dyson's adjoint applied 4 times produces the partition 3 plus 3 plus 1 plus 1, which is the mapping between partitions that finds partitions with rank 2r plus 1 or 2r, and the partitions in odd parts. I close on this because of the 3 topics that I've described this morning. Of the 4 topics, the first 3 have had, other people have carried into what everyone would agree, by any definition, into very deep and significant applications. The adjoint, however, has perhaps been temporarily asleep, and so I wanted to at least end with that because I think this was a profound observation and utilizable not just in something like proving Nathan-Fine's theorem, but in a variety of other possibilities. And I think that that is the point at which I should stop. Thank you very much.